Right. Good afternoon, class. Welcome back to System Programming class. Let's get started. So today is Tuesday, so we're gonna solve the attendance quiz. But before solving this quiz, let's check the survey Q&A session. So the first question was, where is the result returned by a child process to its parent process stored? So when the child process exits, we can send this exit status to a parent process, right? And to get the child process's exit status, we have to use this wait or wait PID function. And during this progress, this exit status value will be stored in kernel memory space. So yeah, so the answer is kernel memory space. And through this exit status, we can only hand the one integer value to the parent process. So we cannot hand much data through this process. However, if you want to send more data to the parent, we have to use inter-process communication, which we will learn today. So today's topic. So, and the second question was, could you show us pthread example? So yeah, I prepared a simple pthread example. I didn't prepare live demonstration for the pthread. So here is the code, and when you want to use the thread in Unix system, you have to use this pthread. And unlike the process, when we generate the process, we use the fork function, and it copies the whole things of the parent process. However, when we use the thread, we will define some worker function for the specific thread. So unlike the process generation, we will simply the threads will simply copy this text section, and it will perform only this function. So yeah, to create the thread, we will use this pthread create, and to use this function, we have to specify the worker function. So yeah, by using this pthread creates, we can generate two thread workers, and they will print out these messages. And after the thread, the parent process can wait the thread's termination by using the thread join. So it is similar to the wait function of the process. So after waiting the process's termination, we will print this our thread finished string. Yeah, so I prepared the pthread example. And the third question was, will there be coding on the exam? Yeah, there will be. I will give you some code to understand or predict some result. So, however, there will be not a problem. There will not be a problem where you have to fully write down the code. So the exam style will be similar with the military exam. So yeah, that's it. And what day will the quiz be next week? I don't get the purpose of this question. We have been solving the attendance quiz on Tuesday, right? So I don't understand this question. Yeah, and the last question was during the demonstration, when you paused and then listened execution, 10 seconds had already passed. Was that because it continued running in the background? So this sleep function, it measures the 10 seconds independently of the pause. So if you understand how this sleep function works, then you can understand this situation. So this sleep function measures the work clock time. So even if we pause the program, the work clock, our time goes, right? So work clock doesn't stop. So that's why when we resume the execution, 10 seconds had already passed. Okay. Ah, it was not the last question. So the last question. Assuming that we can create multiple threads, I think there will maybe no performance benefit because the number of CPUs is fixed. Is creating multiple threads a way to achieve other additional purposes? Without the the performance, there are some many benefits to use the thread. So thread can improve the responsiveness, and um, during the I/O operation, when a thread when a thread or when a process has to read or write from some files, they have to wait the write or read of the file, and during that I/O operation time, other threads can execute, and it can increase the performance. And also, context switching between threads is usually cheaper than that of the processes. And most importantly, using thread can increase the CPU utilization. So even if you have multiple CPUs, if you do not use the threads, then you can only use one CPU, only one CPU core. So by using multiple threads, you can fully utilize the CPU cores. So yeah, thread, they can give huge performance benefit. Yeah, so that's all for the Q&A session. And yeah, I prepared 5 attendance quiz, so let's solve them. I give you 5 minutes. Recently, I have posted the quiz scores, right? And for your information, late submission is not allowed. So you have to please care about the deadline. So for the late submission, I give you 0 scores. Yeah, there was some questions or emails related to the late submissions. Okay, time's up. So today's problems were not difficult, right? And we have already solved this question 3. I don't want to explain it again, so I'll just let you know the answer. If you forgot how to solve this problem, please refer this answer and solve by yourself in your home. Okay, then let's start today's lecture. So today we're gonna study inter-process communication, message passing, shared memory, signals, and pipes. And in the next class, we're gonna study some communication in client and server systems, such as networking. So in the next class, we're gonna study sockets and RPC. And for the detailed explanation, you can refer the textbook. So why do we have to support this inter-process communication? Inter-process communication means that we can send and receive some data or information among the process. So one process can send some data to other process. That is the inter-process communication. So we have to support the inter-process communication for this process cooperation. So if some processes want to cooperate, we have to support the inter-process communication. And there are some reasons for providing on this process cooperation. So for the process cooperation, we have to support information sharing. So we have to allow concurrent access to some information. So good example is copying and paste. For example, if we copy some text from a word processor and paste it to the web browser, that is a inter-process communication. We copy some data from a word process and copy that data to the web browser, another process. So that is so to do that, we have to support this information sharing. And process cooperation can speed up the computer. So if you want to run some particular tasks faster, we have to break them into subtasks and executing them in parallel. Then we can increase their performance. Yeah, so we can, for the computation speed up, we have to support the IPC. And also for the modularity, so we have to support the IPC. The modularity means that we can split some functions and attach and break them separately. So the cooperating processes require some inter-process communication, and we can do this inter-process communication through 2 models, shared memory model and message passing model. And most operating systems support both of them. So let's see the shared memory first. So we can support IPC through memory sharing. So it means the shared memory means that we will establish a region of shared memory. So normally, operating system try to prevent one process from accessing another process's memory. So I can access the data or memory address of other process, and also other process cannot access my memory region. That is normal in operating system. However, for the shared memory, multiple processes can access the same memory region. So by removing this restriction, we can support the inter-process communication. So typically, the shared memory region resides in the address spaces of the process, and like this. So we have to allocate this shared memory region by some process, and so processes can use this some shared memory creation function and attach functions to create and gain access to the shared memory regions. And after creating this shared memory region, processes can exchange information by reading and writing the data in the shared regions. And the form of data sharing and managing the location and data format, they are the things will be determined by the processes, not under the OS's control. So operating system just support the memory allocation, and how do we read and write the data will be handled by each process. So this shared memory approach can be faster than that of the message passing because after the shared memory creation, we don't have to call the system calls. So kernel will not be invoked during this shared memory uses. So once established, our access will be treated as a routine memory access. So we don't have to depend on assistant from kernel. So because kernel is not intervented, its speed is faster than that of the message passing. However, the shared memory's major issue is how to provide mechanism and manage the synchronization. So we're gonna see this issue. So there is a producer and consumer problem. It's a common paradigm for cooperating of processes. So at here, producer means so a producer will produce some information or data, and then the data will be consumed by a consumer process. So here is an example. Compiler may produce assembly code, and this assembly code will be consumed by an assembler. And then the assembler will take this assembly code and then produce object modules, and it will be consumed by the loader. So in this context, assembler is a producer and loader is a consumer. So this consumer and producer problem is also exists in client and server paradigm. So we generally consider a server as a producer and client as a consumer. So for example, when we access a web browser, and so when we go to some website, a server will generate some HTML codes and images, and we, the consumer, will take this information and consume to render the websites, right? Yeah, that is the consumer and producer problem. So this producer and consumer problem is also they also access in shared memory. So we have to handle the this producers and consumers. So one solution to handle this producer and consumer problem is to allow producer and consumer run concurrently. We must have a buffer to fill the data generated by producer and emptied by the consumer. So this buffer will reside in a region of the shared memory. So producer will generate the data and consumer will consume the data. And during this process, we have to care about this produced and to be consumed data. And this data will be temporarily saved in the buffer. And there is two types of buffers. unbounded buffer and bounded buffer. Simply, bounded means limited. So bounded buffer assumes a fixed buffer. So the consumer and producer have to care about its mixed size, its fixed size. So producer must wait for the producing, if the buffer is full. When the buffer is full, we cannot add more data into the buffer, right? So producer have to wait. And when the buffer is empty, consumer have to wait for the producer to generate some new data. However, as for the unbounded buffer, there is no practical limit on the size of the buffer. So the consumer still have to wait for new items if the when the buffer is empty. However, the producer can always produce new items because there is no limited buffer size. The buffer size is unlimited, so that is the difference. And then let's see how the bounded buffer illustrates IPC using shared memory. So let's say that this following item, the buffer, is reside in a region of memory shared by the producer and consumer processes. So let's say these three items, buffer, in and out, they reside in region of the shared memory. Then we can save some items as much as buffer size in the buffer. And this shared buffer is implemented as a circular array or circular queue with two logical pointers, in and out. So I prepared the example. So let's say the buffer size is 5. Then we will have these kinds of circular array. So when two pointers are pointing the same point, so this pointer and this pointer, in and out, they are pointing the same location first. It means that when the buffer is empty, it means the buffer is empty. When in equals out, then it means buffer is empty. So there is no values. And when we add a new value, then when the new value is added, then the location of in pointer will be added. So the previous location of the in pointer was first. However, after the inQ function, its location will be added as much as 1. Yeah. So this input in points to the next free position in the buffer. So when the new value is produced, then its location will be in pointer's value, and the value of the in pointer itself will be added as much as 1. Yeah, like this. And when we dequeue, when a consumer consumes data of a buffer, and then the data will be reduced, and the my bad. So it's not a, it's a stack, not a queue, right? It's a stack, not a queue. I prepared a long example. So when we dequeue, then this. So in this situation, when we dequeue the value, not 30, 10 should be removed, right? Because it is a queue. So 10 will be removed, and the location of out will point this 20, the second value. So 10 will be removed, and yeah, that is the right thing. So it will be when we dequeue this circular queue, the 10 will be removed, and the location of out will be changed. So 30 will not be dequeued, and also the location of the in pointer will not be changed. So okay, next time I'll prepare the example again. So yeah, that's how we handle the circular queue. So the buffer is empty when in equals out, and it is full when this equation holds. Yeah, so in that manner, we will add some values to the buffer. And then let's see these two codes, the codes for the producer and consumer processes respectively. So the producer will produce some data, and it will save the data into the buffer. So we have to add new data into the buffer, and we have to move the location of the in pointer. And consumer will consume a data, so we will take out one element from the buffer, and we will manage the location of the out. So it's very intuitive, right? However, there is two while loops. Can you guess the meaning of these two while loops? Without this code, without this while loops, we can add and dequeue the data from the buffer. Then why do we need this simple while loop? Actually, this while loop doesn't have any internal comments, internal instruction, right? Just a one while loop. Then why do we have to use this two while loops? So let's go back to the previous slides. So the buffer is empty when in equals out, and buffer is full when this equation holds. So it checks whether the buffer is full or not, and this loop is checking whether the buffer is empty or not. So the size of the buffer is limited, right? So when the buffer is full, we cannot add more data to the buffer. So this loop is for waiting. So when the buffer is full, because we cannot add more data to the buffer, the producer will wait consumer to consume the buffer, the data. So that this buffer is access for the buffer to not to be full. And when the buffer is empty, we cannot read any data, right? So this while loop is checking the empty, right? So because there is nothing to read, so the consumer will just wait producer to produce new data. So the meaning of these two loops. So the first one is if the buffer is full, the producer waits, and the second loop means if the buffer is empty, then the consumer waits. Yeah, so we have checked how producer and consumer have to be treated. And actually, to use the shared memory function, to use the shared memory, we have to declare the shared memory region, right? And we were gonna see this POSIX standard shared memory functions. So by calling these three instructions, we can use the shared memory. And these shared memory regions will be organized using memory method files by using mmap, and it's associated with the region of the shared memory with a file. So to use the shared memory shared memory, firstly we have to open the shared memory. So we will use this function, shared memory open, and it takes the name of the shared memory object and some permissions. So the second parameters means the permission of the shared memory region. So if if these names of shared memory is not created, then we have to create the new shared memory. So it's for the creation permission, and for reading and writing the shared memory, we have to also get this read and write access. And the last parameter is relevant to the file access permission. So by calling this, we can create the shared memory region, and we will get the integer file descriptor. Also, this function returns a file descriptor. Actually, they will not be used like real files, like through read and write function. And when we get after getting the file descriptor, we have to declare the size of the shared memory. And by using this ftruncate function, we can set its size. And after setting its size, we can map the memory region as a file through this mmap. And so after calling these three functions, we can have the shared memory region. And for the detail, you can read these parameters on your own. Okay, then let's see a real example code. So I prepared POSIX producer and POSIX consumer. So actually the meaning of the code is very easy. So we have some size and some messages. So we're gonna write down this hello world into the shared memory region. And so to use the shared memory, we have to create a shared memory object by calling this. And then we will configure the size of the shared memory by calling this. So the size of the shared memory is 4096 bytes. And after setting the size, we will map the memory into the shared. We will memory map the shared memory object as a file. So after calling this mmap, we will have a shared memory region in the memory space. So and the size of the shared memory is 4096 bytes, and this pointer PTR will point the start of the shared memory. And so now we have this shared memory, and then we can by using this fprintf, it's a function that writes a formatted string into a memory buffer. So by calling this, we can write down this hello into the shared memory. And because after writing this message, the location of the PTR is not changed. So we have to manually change its location. So we will add as much as the message's length. So we have to move the PTR. And then we will write down the remaining string, word. So if we do not change the location of the PTR, the second string, word, will be overwritten in this area. So we have to move the location of the PTR. And here is the POSIX consumer. So because we have already created the shared memory object at here, like here, we don't have to create the shared memory object again. So at here we requested creation permission and read and write permission. However, this is a consumer, right? So it doesn't have to write the shared memory, and we don't have to create the shared memory. So we only need the read permission. However, still we have to open the shared memory object. And then, because the size of the shared memory object is already configured at here, right? So we don't have to configure the size of the shared memory again. So we don't need f_truncate here. However, we still have to memory map the shared object. So by calling this mmap, we can have shared memory which have hello and world 2 strings, and like using the memory space, we can simply call this ptr to read the whole string. So after calling this mmap, the ptr will point the start of the shared memory. Yeah. And after using the shared memory, we can remove the shared memory object by calling this onLink function. Okay, that's all for the shared memory. Any questions so far? Okay, good. Then let's see the message passing. So we can support the IPC through this message passing systems. Its communication takes place by a means of message exchange. So messages will be exchanged between processes, either directly or indirectly through a common mailbox, like this mailbox. And it is easier to implement in a distributed environment than the shared memory. So in a distributed environment, or in the distributed systems, process A and process B can have different memory address. In the system, we cannot easily use the shared memory because their memory space is different. So in that case, this message passing system will be easier to implement. So in a distributed environment, process can have different memory spaces. So we have already seen this the term message passing when we have studied microkernel, right? So for the distributed environment, because microkernel suppose the distributed environment, they use this message passing. And also they are used for exchanging smaller amounts of data because no conflicts need to be avoided. So as for the shared memory, many processes can write the shared memory at the same time, right? So we have to care about the conflicts. However, when we use the message passing, we don't have to care about that. So there is no conflicts need to be avoided. Okay. So if process P and Q wants to communicate, then they need to establish some communication link between them for the message passing. And typically, this link will be implemented through the system calls. So the kernel must be involved in sending and receiving messages. So unlike the shared memory, when we send the message and when we receive the message, the kernel will be invoked. So the speed of the message passing is slower than that of the shared memory. And for the message passing, we have to implement some logical implementation of communication link in a variety of ways. So we can have a direct or indirect communication. Under the direct communication, processes must name each other explicitly. And if you use the indirect communication, messages are sent or received from mailboxes or ports. So you don't have to explicitly specify the other processes like this. And also we can we have to implement synchronous or asynchronous message passing. So we can have blocking and non-blocking send, and blocking receive, and non-blocking receive. So non-blocking and non-blocking send and non-blocking receive means that you can always send the message and you can always receive the message. So sender sends the message, always send the message when you use the non-blocking send, and when you use the non-blocking receive, receivers gets a message, always get the message. So if the buffer is empty, then it will gets the null value. However, blocking send and blocking receive cares for the status of the opposite part. So sender waits until the message is received, and receiver waits until a message arrives. So yeah, that is the blocking and non-blocking send. And for the message passing, we also have to care about the size of the buffer. So buffer can be zero capacity, or bounded capacity, or unbounded capacity. So I summarized the buffer capacity and the desired behaviors of sender and receiver. So when the buffer capacity is 0, then we cannot temporarily save the sender's data, right? So sender have to use, and also receiver have to use the blocking send and blocking receive, because there is no buffer. Sender have to wait until the receiver gets the value, and receiver also have to wait until the sender's data is arrived. So it always have to use this blocking send and blocking receive. And for the bounded capacity, you can use both blocking and non-blocking send and receives. However, it is desired to use the blocking send and blocking receive when the buffer is full or buffer is empty. And for the unbounded capacity, because the capacity is unlimited, so sender doesn't have to wait for the receiver. So in this case, the desired behavior of the sender is non-blocking send, always sending the data to the buffer or to the sender, either to the receiver. So there is so many implementing ways to do the message passing. However, all these things will be supported by the kernel, so we don't have to care about that. So the solution to the producer and consumer problem using message passing becomes very easy. So here's an example. Unlike the shared memory, we can just simply use send and receive function. We don't have to care about the buffer size. All these details will be carried through the kernel, the system code. So inside this send function, the blocking and unblocking behavior will be handled. So, so this producer and consumer problem becomes very easy. So, yeah, we can simply call the send and receive function. Yeah, so that's all for the message passing. Then what about IPC in Linux? So they support shared memory and message passing or message queue. And there is one more thing, mechanism for notifying process about a particular event occurs. That is a signaler. So let's see this signaler first, and then we're gonna check these types at the end of this class. So signal is a sort of IPC mechanism to notify a process of a particular event. So unlike other things, so you by using this shared memory, message queue, or pipes, you can send and receive lots of data. However, through this signal, we can only send only one integer value. So by sending this one integer value, we will notify a process of a particular event. So these signals can be thought as a software interrupt. So the signal will be generated by a particular event and will be delivered to the process. So a good example of a signal is control plus C. When we run a C program and when we type this control C, the process will be terminated, right? That is sending a signal to the process. So by typing this control plus C, we are generating a signal to terminate the process. So it's a signal. It's a good example of a signal. So signal handler will take this signal and then process this signal. So every signal has a default handler that kernel runs when handling signal. So so when we press this control plus C, this sig into signal will be passed to the current running process, and the default signal handler will take this value 2, and then will terminate the current running process. Yeah, so every process has a default signal handler, and we can add our custom signal handler to our program. So by using this header and by using this struct and this function, we can have our custom signal handler. So in this example, it just takes this sig alarm. It will take this sig alarm signal, and it will simply print the number of the signals. And we can send a specific signal to process by using this kill function. So the kill command can be misleaded because its name sounds like it always terminates the process. However, we can use kill command to send some specific signal to other processes. So the default operation of kill command is just sending this sig term to the other process. So for example, when we type some kill and some PID, then this sig termination will be handed to this process. And then this process will handle the sig term. However, by adding some options like sig int, we can hand other signals to the process. For example, like sig pipe and process ID, we can hand this number 13 to this process 1, 2, 3, 4. So the meaning of kill command can be misread. However, it actually, the lore of the kill function is send a specific signal to a process. And a process can define its own signal handler for some signals. So for example, a process can catch or ignore this sig term. So if you want to build a process or function that still, if you want some very strong program, you can add your own signal handler to ignore this SIG term. Then, so in the case, then even if you press the Control C, then it can ignore this SIG int, and the program will not be terminated. So therefore, if you fix the signal handler, the kill may not terminate the process if the SIG term is handled or ignored through your own SIG handler. However, some malicious user can use this signal handler very badly, right? So to prevent that, SIG kill and SIG stop cannot be caught, handled, and ignored through the signal handler. And when you type this man7 signal, you can see some basic definitions of many signals. We are familiar with this Control plus C, and we usually see this SIG-sec when we access some wrong memory address. And also we have some user-defined signals for the users. So the meaning of these signals are not defined. So users have to define their meaning through this their own signal handler. Okay, that's all for the signal. And lastly, let's see the pipe. We have already seen this pipe before, right? We can use this pipe for the I/O redirection. However, pipe also can be used for the inter-process communication. However, their operation is bidirectional. So this is a pipe. So when we use a pipe, the water will be flow for one direction at a time, right? Water cannot be flow this way and this way at a time, right? So the operation of the pipe is bidirectional, basically. And there is two common types of pipes used on both Unix, Linux, and Windows systems: ordinary pipe and named pipe. So let's see the ordinary pipe first. So ordinary pipe allows only one-way communication, unidirectional, and requires a parent-child relationship between communicating processes. So this pipe will be used for between child and parent. So when we see the example, you can see that the fork function will be used. So by calling this pipe function, we can have this two file descriptors, ft0 and ft1. So ft1 will be used for the read, and ft1 will be used to ft0 will be used for the read, and ft1 will be used for the write. So producer writes to the one end, ft1, and consumer reads from the other end, the ft0. So data will be always flow like this, from the write end to the read end. And so that's the key concept of the pipe. And then let's see the example code. So to use the pipe, we have to declare some the read end and write end. And by using this pipe function, after using this pipe function, we can have pipe ft 0 and 1, and pipe FT 0 will be read for the will be used for the read, and pipe FT1 will be used for the write. So in this example, we want to treat parent as a producer, and we want to treat child as a consumer. So parent will use this write hand, and child will use this read hand. So child process has the FT1 and parent process has the FT0, but they will not use that. Parent will only use this write hand, and child process will only use this read hand. So in this example, parent will send some data to the child process. And after the fork, both processes have the FT0 and FT1. However, a child process will only read from the pipe, so it doesn't need the FT1. FT1 is the right hand, so and we don't need, the child process doesn't need it. So because this right hand will not be used, we will directly close the FT1 at the child process. And when it comes to the parent process will only write some data to the pipe. It will not read from pipe. So we don't need, the parent process doesn't need the read end. So we will directly close the FT0 at the parent process. And we can write down the some data to the pipe by using this. And after the data sending, we will close the pipe. And in the consumer side, the child process, it will wait for the data to be written, and when the data is written, then it will read the data from the pipe, and it will also close the pipe and then exit. So the treating pipe is similar to the treating file systems. So we can use this write function, unlike the message passing or shared memory. So that is the ordinary pipe. However, they require this parent and child relationship. So only parent and child can use this pipe function. So if there is no child and parent relationship, you cannot use this ordinary pipe. So to this end, we have named pipe. So it provides a much more powerful communication tool than ordinary pipes. So communication can be bidirectional. So one pipe can be flow like this and this. However, only half duplex transmission is permitted. So you cannot send and receive data at a time. It's like a walkie-talkie, in Korean, 무전기. So communication can be bidirectional. However, they only support the half duplex communication. So where data can flow in both directional, but only one direction at a time. And no parent-child relationship is required between communicating processes. And once it is established, several processes can use it for communication. So unlike the ordinary pipe, every process can use this named pipe. And this named pipe stays alive even after communicating processes terminate. Differently, the ordinary pipes stop to exit when the process have finished communicating and have terminated. However, the named pipe will stay alive even after the process terminated. So we have to manually close this named pipe. In the Unix system, you can use this named pipe by calling this mkFIFO, make FIFO system call. As I told you, the pipes can be handled like the ordinary file I/O systems. Like so, you can read and write pipe by using this write or read function, and yeah, they are only half duplex transmission is permitted. So I prepared an example. So to use this named pipe, you have to use this mkFIFO. So it's my named pipe. It's my own named pipe, and it's very similar to handling file system. So echo hello. So when we type like this, we can generate some file, right? So like handling the file system, you can easily send some data to the named pipe. And when the data is transmitted to this named pipe, you can run a new other process by simply reading some read value from this pipe. You can get the transmitted data, and because after the communication and after the after the communicating process is terminated, the named pipe is still alive. So to remove the pipe, to remove the named pipe, we have to explicitly delete the named pipe from the corner. So this command is deleting the named pipe from the corner. Okay, so that's all for today. Any questions so far? Okay, then before ending up this class, I will take a survey. Okay, it's hard to read, so I will answer this question later, next class. Okay, it was easy. Okay, that's all for today. See you next time.